Hi everyone, welcome to International Conference on Fluid Flow and Thermal Science. My name is Mohammad Hojjat. I'm an assistant professor of chemical engineering at University of Isfahan in Iran. I started working on the behavior of nanofluids in a research team led by Professor Etemad at Isfahan University of Technology when I was a PhD candidate. After graduation, I kept in touch with Professor Etemad and some other members of the group and did independent collaborative research works. We have comprehensively investigated the thermal behavior and hydrodynamic of Newtonian and non-Newtonian nanofluids in circular tubes, non-circular ducts, shell and tube with exchanger, double pipette exchanger, oiling and free convection. We also proposed some empirical correlations and artificial intelligence models for behavior of nanofluids. I am delighted to be here to talk to you about the nanofluids and their applications. My presentation is divided into 5 parts. I'll start with an introduction and briefly talk about nanofluids and the pros and cons of using them. Then the common methods of preparing nanofluids will be explained. Next, I will describe the most important applications of nanofluids by focusing on the works done by our research team members. Then I'll explain the main challenges in application of nanofluids. And finally, I will suggest some work recommendations. Efficient heat transfer systems are an obvious current and future need of many industries, such as microelectronics, transportation, space, and defense. There are several methods for heat transfer enhancement. One of them is to improve the thermal behavior of heat transfer fluid. As shown in this figure, thermal conductivity of most solids are order of magnitude higher than that of most heat transfer fluids. So adding solid particles to the fluids improves their thermal conductivity. But the presence of large particles in the scale of micro and millimeter causes some problems. Particles with these dimensions settle quickly, and the resulting suspensions are not stable. Severe erosion of equipment is another problem with such particles. Due to clogging, the use of small duct is impossible. Falling is a major problem. And finally, high pressure drop is a disadvantage of using suspensions containing milli or micrometer sized particles. With the advancement of material science, it has become possible to produce particles with nanometers dimensions. Nanoparticles have unique properties. Many properties of particles are functions of their sizes. So some properties of nanoparticles, such as color or conductivity, may differ from the bulk properties. Nanoparticles have the specific surface areas of 3 orders of magnitude greater than that of the microparticles. For a given of mass, the number of particles increases as their size decreases. About 20% of nanoparticle atoms are near their surface. For the first time in 1995, Choi dispersed nanoparticles in a fluid and called it nanofluid. Thus, suspensions of ultrafine particles of nanometer dimension in conventional heat transfer fluid are referred to as nanofluids. Various kinds of nanomaterials have been used in preparing nanofluids. Oxide ceramics, metal carbides, nitrides, metals, nonmetals, layered and functionalized nanoparticles. Base fluids include water, ethylene or triethylene glycol, and other coolants, oil and other lubricants, biofluids, polymer solutions, refrigerants, and other common fluids. In summary, by adding nanoparticles to conventional heat transfer fluids, a new generation of heat transfer fluids was generated, which called nanofluids. Nanofluids have some potential benefits such as high specific area and therefore more heat transfer surface between particles and fluids, high dispersion stability, reduced pumping power as compared to pure liquids to achieve equivalent heat transfer intensification, reduced particle clogging as compared to conventional slurries, adjustable properties including thermal conductivity, surface wettability by varying particle concentration to suit different applications. The preparation of nanofluids is a key step that determines their stability. According to colloidal theory, sedimentation in suspension ceases when the particle size is below a critical radius, due to counterbalancing of gravity forces by the Brownian forces. Application of smaller size of nanoparticles help us to prepare stable suspensions. However, due to high surface area and surface activity, nanoparticles have a tendency to aggregate. The preparation of stable nanofluid is one of the most important challenges in the practical applications of nanofluid. Two methods are used to prepare nanofluids: the two-step method and single-step method. In two-step method, the nanomaterials, as are nanoparticles, nanotubes, and nanofibers, are first produced either by a physical or chemical process. The dry powder is then dispersed in a fluid to form nanofluid. In single-step method, nanoparticles are produced and dispersed in base fluid simultaneously. In this method, the aggregation of nanoparticles is minimized and the stability of nanofluid is increased. There is no comparison available for nanofluid produced by the single-step and two-step method, but it can be said that for nanofluid produced by single-step method, the production cost is high as compared to the two-step method. Controlling the particle size in the nanofluid is difficult and the particle size is not uniform. Another drawback is that some of the reactants are left in the nanofluid due to incomplete reaction, which are difficult to remove. Since synthesis methods are available to produce nanoparticles with a wide range of sizes at commercial scale, the two-step method seems to be the most economic method of producing nanofluids for large-scale applications. Now I explain various applications of nanofluids according to available literature with a focus on the results of our research group. As mentioned, the main idea of the invention of nanofluids was to improve the thermal behavior of conventional heat transfer fluids, so their most important application is to improve the performance of heat transfer equipment. One of the characteristics of fluids that determine their thermal performance is the thermal conductivity. The thermal conductivity of nanofluids depends on some factors such as particle concentration. Almost all previous studies show that the thermal conductivity increases with particle loading. For example, this figure, which shows the experimental results of the thermal conductivity of non-Newtonian nanofluids obtained in one of our investigations, indicates that the thermal conductivity of nanofluid increases by increasing nanoparticle concentration. For these nanofluids, thermal conductivity does not increase significantly with the concentration of nanoparticle up to concentration of 1.5 volume%. This may be due to the large apparent viscosity of nanofluids, which limited the mobility of nanoparticles. Experimental results of previous investigations suggest that the cylindrical shaped nanoparticles showed higher enhancement than the spherical shaped one for the same base fluid, and that the enhancement in thermal conductivity increases by particle aspect ratio. Particle material and the base fluid are the other factors affecting the thermal conductivity of nanofluids. This figure shows the thermal conductivities of various nanofluids. For water-based nanofluid, MWCNT nanofluids has the highest thermal conductivity, whereas silica nanofluid has the lowest thermal conductivity. This result shows that the thermal conductivity enhancement of nanofluid is higher for nanoparticles with higher thermal conductivity. In case of copper oxide nanofluid, the thermal conductivity enhancement of ethylene glycol-based nanofluid is higher than that of water-based nanofluid. Therefore, adding nanoparticle is more effective for a fluid which has lower thermal conductivity. The thermal conductivity of nanofluids depends on the temperature. The thermal conductivity of nanofluid increases with increasing temperature. Because Brownian motion and clustering, which are important factors affecting the thermal conductivity of nanofluid, are significantly influenced by temperature. One of the important physical parameters which play a major role in nanofluid thermal property and the stability is the nanoparticle size. Based on the published experimental data, the thermal conductivity of nanofluids increases with decreasing particle size. Some additives, such as surfactants, are used to keep the nanoparticle in suspension and prevent them from agglomeration. Thus, they are expected to cause thermal conductivity enhancement of nanofluids. Most of the reports show that the optimum concentration of additive will strongly enhance the effective thermal conductivity of nanofluids. The pH at which a molecule or surface carries no net electrical charge is called the isoelectric point. At this point, the repulsive forces between the particles are reduced to zero, which increase the possibility of agglomeration. The effective thermal conductivity of nanofluid increases with the difference between the pH value and the isoelectric point of nanofluids. Clustering is another parameter which can affect the thermal conductivity of nanofluids. Clustering of nanoparticles can create paths of lower thermal resistance and enhance the thermal conductivity significantly. Heat can move very rapidly within such clusters and increase the thermal conductivity effectively. However, in general, clustering may have a negative effect on heat transfer enhancement, especially at low nanoparticle concentration, by settling the small particles out of the liquid and create large region of particle-free liquid with high thermal resistance. Viscosity is an important property, particularly concerning fluids flowing in a tube in heat exchanger, because the pressure drop and pumping power depends upon it. In this regard, many investigations have been carried out to determine the empirical and theoretical correlations for the estimation of viscosity of nanofluids. It should be noted that the most of instruments that have been used for measuring the viscosity of nanofluids were developed and calibrated using homogeneous fluids. Rotating viscometers, falling ball viscometers, and capillary viscometers are the instruments used to determine the viscosity of nanofluids. Researchers developed several models. Many experiments have been conducted for verification of these analytical models, but there are few models that predict the viscosity of nanofluids well. The effective viscosity of nanofluids depends on the viscosity of the base fluid. Other factors that affect the viscosity of nanofluids are the particle concentration. Most of investigations available in the literature on the viscosity of nanofluids regarding the effect of nanoparticle concentration agree upon the fact that the viscosity of nanofluids increases with the increasing particle concentration. It's also important to know how the viscosity of nanofluids changes with temperature, because for commercial applications of nanofluids in heat transfer equipment, viscosity at different temperatures is required. In this regard, many researchers have studied the effect of temperature on the viscosity of nanofluids and found that with increasing temperature, the viscosity of nanofluid decreases. Contradictory results have been published about the effect of nanoparticle size. The results of some studies show that the viscosity of nanofluid decreases with increase in particle size, while the results of some studies show the opposite. It's observed that the particle size effects are more significant for high particle concentration. There are very few results about the effect of particle shape on the viscosity of nanofluids. However, viscosity of nanofluids is strongly dependent on nanoparticle shape. Results of previous study report that elongate particle-like platelets and cylinders results in a higher viscosity at the same particle concentration. Shear rate is another parameter which can influence the viscosity in non-Newtonian nanofluids. Experimental results of some investigation on the viscosity of nanofluids show that the nanofluid exhibit different rheological behavior at different particle loadings. Newtonian behavior at low particle concentration and non-Newtonian behavior at high concentration. Also, an increase in thermal conductivity and changes in other physical properties such as density, heat capacity, and viscosity are important indications to infer an improved heat transfer behavior The heat transfer coefficient is truly the main feature of nanofluids that plays a key role in heat transfer performance. Results of almost all previous investigations show that the heat transfer coefficient of nanofluids is higher than that of the base fluid and increase in nanofluid concentration. We studied the convective heat transfer of three types of non-Newtonian nanofluids containing alumina, copper oxide, and titanium nanoparticles in a horizontal circular tube with constant wall heat flux in laminar flow condition experiment. An aqueous solution of CMC was chosen as non-Newtonian base fluid. The average heat transfer coefficient of alumina nanofluids is plotted as a function of Peclet number at different nanoparticle concentration. It's clear that addition of nanoparticles to the base fluid enhances its heat transfer coefficient significantly. At a given nanoparticle concentration, the heat transfer coefficient of nanofluids increases with increasing Peclet number. The ASET number of nanofluids also increases with nanoparticle concentration and Peclet number in the same manner. Enhancement of the effective thermal conductivity is an important factor that causes the increase of convective heat transfer coefficient of nanofluids. But based on our results and the results of other researchers, the enhancement of the heat transfer coefficient of nanofluids is much more than that solely attributed to the thermal conductivity enhancement. This shows that some other factors also contribute in the enhancement of the heat transfer coefficient. In this figure, the local heat transfer coefficient of alumina nanofluid is plotted as a function of axial distance from the inlet of the test section at different nanoparticle concentration, for Peclet number of about 140,000. It's observed that at a certain Peclet number and nanoparticle concentration, the local heat transfer coefficient of nanofluid decreases with increasing axial distance. And at a given Peclet number and axial distance from tube inlet, the local heat transfer coefficient of nanofluid increases with increase in nanoparticle concentration. These results show that the entrance region for nanofluid is longer than that of the base fluid and increasing by increasing nanoparticle concentration. This is due to decreasing thermal boundary layer thickness of nanofluid relative to that of the base fluid. Similar trends were observed for other nanofluids and other Peclet numbers. The local heat transfer coefficient is directly proportional to the thermal conductivity of the fluid and inversely proportional to the boundary layer thickness. This means that the enhancement of thermal conductivity of nanofluids and or decreasing the thermal boundary layer thickness increases the heat transfer coefficient. As mentioned, the enhancement of heat transfer coefficient of nanofluid is more than the effect of improving the thermal conductivity, which may be the result of reducing the nanofluid thermal boundary layer thickness. The thermal dispersion due to the random motion of nanoparticle also contributes to this enhancement, which in turn results in a flat temperature profile. As a result, the temperature gradient at the wall becomes steeper and the heat transfer rate at the wall increases. Some other factors such as hermaphoresis, collision of nanoparticles, and slip velocity between the fluid and nanoparticles could also be responsible for the heat transfer coefficient enhancement. We also studied the performance of alumina water and titanium water nanofluids as coolant in horizontal stainless steel shell and tube exchanger in turbulent flow regime. Here you see the overall heat transfer coefficient of nanofluids plotted against the Peclet number for various volume concentrations. As you see, the overall heat transfer coefficient of nanofluids increases significantly with Peclet number. The overall heat transfer coefficient at a constant Peclet number increases with increasing nanoparticle concentration and then decreases. In other words, there is an optimal concentration for each nanofluid. At different nanoparticle concentrations, the heat transfer enhancement of nanofluids are not the same. Thermal performance of titanium in water nanofluid is better at lower particle concentration and alumina water nanofluid at higher concentration. The difference between the thermal conductivity and size of nanoparticles may be the source of this behavior. In another research, Nasir et al. Investigated the heat transfer behavior of nanofluids through an annular channel under constant wall temperature condition and turbulent flow regime. The base fluid was water, and nanoparticles used were alumina and titanium oxide. The Nusselt number of nanofluids for different Peclet number is shown. Both nanofluids show higher Nusselt number than that of the base fluid, and enhancement increases with nanoparticle concentration. Comparison with previous study on the heat transfer enhancement of nanofluids in circular tubes show that the enhancement of Nusselt number is lower for concentric annular channel. As mentioned before, the enhancement of Nusselt number reveals that the heat transfer performance of nanofluid is under influence of various parameters, and the thermal conductivity is not the only main factor. Nanoparticles migration, Brownian motion of nanoparticles, and decrease in thermal boundary layer thickness, and possible slip condition on the wall are other possible reasons for enhancement of heat transfer coefficient. In order to compare the performance of two employed nanofluids in this research, Nusselt number calculated through the experimental data for concentration of 0.1 and 1.5% are presented. It's observed that there is no significant difference between the Nusselt number of two employed nanofluids. Thermal conductivity of alumina is higher, so alumina water nanofluid is expected to associate with higher heat transfer enhancement. On the other hand, the size of titanium nanoparticle is smaller than that of the alumina. Lower size of nanoparticle results in more mobility of particles and lower boundary layer thickness, and consequently higher heat transfer coefficient. Compromising between these two opposite effects cause almost the same value for employed nanofluid when the nanoparticle concentrations are the same. In an experimental investigation, Nassiri et al. Have studied the heat transfer performance of alumina water and titanium water nanofluid through a square channel with constant wall temperature. The flow regime through channel is turbulent. The effect of nanoparticle concentration and nanofluid flow rate on thermal behavior of nanofluid was determined. They found that at a given Peclet number, convective heat transfer coefficient and Nusselt number of nanofluid are higher than those of distilled water. The enhancement increases with increasing nanoparticle concentration. The results show that the heat transfer coefficient of both nanofluids improve almost equally. Nassiri et al. Have experimentally identified the performance of Newtonian and non-Newtonian nanofluids flowing through a square channel as a coolant. The flow regime was laminar. Two-step method was used to prepare stable suspensions of alumina and titanium nanoparticles. Water and ethylene glycol was used as the base fluids of Newtonian, and the 0.5 mass percent carboxymethyl cellulose in water was used as the base fluid of non-Newtonian nanofluids. Nanoparticle concentration was in the range of 0.1 to 1.5% by volume. The results of various studies show that correlations related to conventional heat transfer fluids are not able to properly predict the behavior of nanofluids. So, two multi-layer feed-forward artificial neural network models were developed according to experimental data. Two empirical correlations are also fitted on the data. Figures depict the heat transfer coefficient of nanofluids obtained from the experiments, and also the values predicted by ANN models and the empirical correlations as a function of Peclet number. The heat transfer coefficient enhances by adding nanoparticles. The enhancement of the heat transfer coefficient is directly proportional to the nanofluid concentration. It's clear that the experimental data and the predicted value are perfectly consistent. The statistical indicators show that the ANN models fitted on the data better than the empirical correlations. Similar trends were observed for non-Newtonian nanofluids as shown in these figures. They also found that for non-Newtonian nanofluids, the improvement in convective heat transfer of alumina nanofluids is greater than that of titanium nanofluids. For non-Newtonian nanofluids, the type of nanoparticles has any remarkable effect on the convective heat transfer enhancement. The performance of nanoparticles for water is much higher than that of ethylene glycol. That is, the base fluid influences the performance of nanoparticles. Improvement in non-Newtonian nanofluid heat transfer in a circular tube is larger at lower nanoparticle concentrations, but it's inverse at higher nanoparticle concentrations. As mentioned before, the results of various studies show that correlations related to conventional heat transfer fluids are not able to properly predict the behavior of nanofluids. So many researchers have proposed empirical correlations and models for predicting the behavior of nanofluids. Here, 4 empirical correlations resulted from our experimental studies are presented. 2 correlations for the laminar flow of Newtonian nanofluids in a square channel, and 2 correlations for the turbulent flow of non-Newtonian nanofluids through a circular tube. Numerous correlations have been presented in other researches that can be found in review articles in this field. In addition to experimental studies, many researchers have used numerical simulations to determine the behavior of nanofluids. In numerical simulation of nanofluids behavior, 3 methods of single-phase, 2-phase, and dispersion have been used. Hojjat et al. Have simulated the steady-state laminar flow forced convective heat transfer of aqueous suspensions of alumina nanoparticles with a diameter of 25 nanometers through an isosceles triangular cross-sectional channel with constant wall heat flux numerically. The geometry under consideration is shown in Figure A. Since the channel is geometrically symmetric, simulations have been performed for half of the channel, as shown in Figure B. Channels with 2 different apex angles of 60 degrees and 90 degrees were considered. Simulations have been made for nanofluids with concentrations of 0.1 to 5 volume%. The hydraulic diameter of all channels is considered to be 1 centimeter. Simulations were carried out based on the single-phase model. The governing equations were solved by using finite volume method. A segregated formulation was adopted to solve the coupled conservation equation sequentially. Average heat transfer coefficient of nanofluids at different nanoparticle concentration as a function of Beckett number for 2 apex angles of 60 degrees and 90 degrees is shown in this figure. As expected, heat transfer coefficient of nanofluids increases with an increase in the Beckett number. The effect of Beckett number on the heat transfer coefficient is the same for both phase fluid and nanofluids. However, the influence of the Beckett number on the heat transfer coefficient is more pronounced in the channel with higher apex angle. This figure indicates the effect of nanoparticle concentration and apex angle on the average heat transfer coefficient. The heat transfer coefficient increases with nanoparticle concentration. This indicated that the effect of nanoparticle on the heat transfer enhancement of both channels is almost the same. The axial velocity profile of fluids on the symmetry surface at 2 positions near the duct entrance and near the end of the channel, fully developed condition, are illustrated here. It's observed that at the entrance of the channel, the velocity profile of all fluids exhibit 2 local maxima near the walls. In order to satisfy no slip condition, the velocity of fluid at the wall reduces to 0 by viscous friction. To satisfy the equation of continuity, the velocity of fluid mass increases in other sections. This increase in velocity cannot immediately reach the center. Therefore, for small values of axial distance, 2 local maxima appear in the velocity profile. By increasing axial distance from the duct inlet, the rise in axial velocity approaches the center of the duct, and the velocity profile will have a maximum. It seems that the location of maximums is independent of nanoparticle concentration, while the value of maximum is a function of nanofluid concentration. This figure displays the effect of nanoparticle concentration on the pumping power of fluids in the channels. The pumping power increases with the increase in nanoparticle concentration for both apex angles. According to the results, the pumping power is affected by the channel apex angle. The average required power for the channel with an apex angle of 90 degrees is almost 20% greater than that of the channel with an apex angle of 60 degrees. Much researches have been done on optimizing the composition of nanofluids and the equipment that use nanofluids. I implemented multi-objective optimization to minimize the total pressure drop and maximize the nanofluid Nusselt number in a shell and tube heat exchanger according to the NSGA2 algorithm. An artificial neural network was developed to predict the thermal and hydrodynamic behavior of two types of Newtonian nanofluids used as coolant in a shell and tube exchanger. Experimental results of our previous work done by Farijullahi et al. That I explained before were used. Input of the ANN model was nanoparticle volume concentration, Reynolds number, nanoparticle thermal conductivity, and Prandtl number. Results indicate that the ANN model predicts experimental data with a very high accuracy. The result that ANN is used in a meta model for evaluating the objective functions for optimization. Nanofluids concentration and Reynolds number were selected as decision parameters. The Pareto front was obtained. The best solution adopted from the points on the Pareto front by two well-known decision-making methods, LinMAP and TOPSIS. Experimental values of Nusselt number of nanofluids against the Pictet number is shown in this figure. Values predicted by the ANN model are also included. It's obvious that the ANN predict the experimental data with high precision. Values of Nusselt number resulted from the experiments and those obtained from the ANN have at most 9% difference. Here the pressure drop of nanofluids is plotted against the Reynolds number. It's observed that the experimental values are accurately predicted by the ANN. Here the Pareto front of the multi-objective optimization is illustrated. The final solution adopted from the points on the Pareto fronts by two decision-making methods are given in table. The Nusselt number of optimal solution are about 30% greater than the base fluid, and the pressure drop of optimal solution are about 10% lower than the base fluid. Many studies have been carried out on the boiling heat transfer of nanofluids. According to their results, the most important factors affecting the boiling heat transfer of nanofluids are surface roughness. Almost all studies show that nanoparticles deposit on the surface and change the surface characteristics. The change in surface roughness is regarded as the main reason for boiling heat transfer and critical heat flux enhancement. The deposition of nanoparticles can increase the surface area and roughness as well as the wettability, which can promote nucleation by vapor trapping and evaporation. The nanoparticle content in the fluid is also an important factor in the boiling process of nanofluids. It can be observed that the roughness of the heater surface increases with increasing the nanoparticle concentration. Most experiments have exhibited positive results. Other factors are ionic additive, heater material, and nanoparticle type. This figure, that is a plot of critical heat flux against the nanoparticle concentration, shows that with the increase of nanoparticle concentration, the critical heat flux increases up to a point, then remain constant. The increase of critical heat flux is more for alumina nanoparticle, which indicates that the nanoparticle material affects the boiling of nanofluids. The size of nanoparticles seems to have negligible influence on the critical heat flux of nanofluids. This can be observed by looking at two curves for nanofluids obtained by dispersing alumina nanoparticles of different sizes in bubble. It's also observed from this figure that the type of nanoparticles does have an influence on the maximum possible increase in critical heat flux. From what I said, it can be concluded that the heat transfer coefficients of nanofluid is higher than the base fluid. Thus, the application of nanofluid in industrial cooling, heating and cooling of buildings, and automotive applications will result in a great energy saving and emission reduction. In a nuclear reactor, the increase of critical heat flux between the fuel rod and the coolant can provide an advantage. In the case of nanofluids, instead of water, the fuel rod would be coated with the nanoparticles and the critical heat flux would significantly increase. Due to the restriction of space, energy and weight in space station, aircrafts and a number of military devices, high heat flux cooling is necessary. Some researchers reported order of magnitude increase in the critical heat flux in pool boiling with their nanofluids compared to the base fluid alone. Further research of nanofluids will lead to the development of next generation of cooling devices that use nanofluids for ultra-high heat flux systems. Nanofluids employed as working medium for conventional heat pipe have shown higher thermal performance. Recent electronics generate an enormous amount of heat, which disturb the normal performance of the devices, reduces reliability and expected life. Therefore, an efficient cooling system is one of the most important problems in designing electronic components. Since nanofluids have high thermal performance and can flow in microchannel without clogging, combined microchannel heatsink with nanofluids have potential as the next generation cooling devices for modern electronic components. The use of nanofluid as absorber fluid in solar collectors have been studied since the last 2 decades. Nanofluids show promising enhancement in thermal efficiency of solar collectors. The use of nanofluids in place of water as base fluid enhances all parameters of solar collectors. The potential of size reduction of solar collector by using various nanofluids is shown in this figure. Compared to water, solar collector's area can be reduced up to 25.6% for copper oxide nanofluids, 21.6% for silica nanofluids, 22.1% for titanium nanofluids, and 21.5% for alumina nanofluids. The application of nanofluids in cooling industries can improve the performance of refrigeration systems and save the running time for refrigeration systems. Nanofluids can also be used in lubrication. The results of some studies show that adding nanoparticles to lubricants improves their performance. Nanofluids may also be used to improve the performance of coating and chemical reactions. Mass transfer is analogous to heat transfer in many respects, and there are close similarities between heat transfer and mass transfer relationships. Since the research results show a significant improvement in thermal behavior of nanofluids, many researchers focus on the use of nanofluids with the aim of improving the mass transfer process. Generally, the researches on mass transfer in nanofluids have been concentrated on gas absorption and liquid mass diffusion. This figure shows the effective absorption ratio in bubble-type absorption. In this type of absorption system, it's somewhat difficult to compare the effective absorption ratio directly due to different conditions in each reference for the nozzle size, absorber configuration, and liquid flow pattern. However, it's meaningful that the absorption performance enhancement by nanofluid is compared and summarized. Many studies have shown significant enhancement in mass transfer. However, a fair number of references have shown a reduction tendency in mass transfer. Brownian motion, interfacial layer, clustering, convection, and the disturbance field created by nanoparticles have been widely provided as the positive contributors to the increased heat and mass transfer. However, exact mechanism of enhanced heat transfer or mass transfer is still unclear. However, results of some investigations show that the mass transfer reduces at high nanoparticle concentrations. Mass transfer is affected negatively at high concentrations by the change of the fluid properties and the nanoparticles' dynamic motion. Some nanofluids, such as zinc oxide nanofluids, exhibit antibacterial properties. Due to improved thermal behavior of nanofluids, they can also be used for more efficient thermal management of fuel cells. Photocatalytic degradation of trichloroethylene in aqueous phase under the UV irradiation in presence of titanium nanoparticles as photocatalyst has been studied experimentally by Shakuri et al. They investigated the effect of nanoparticle concentration, initial TCE concentration, temperature, ultrasonic vibration, agitation, surfactant concentration, and pH on the removal efficiency of TCE. As shown in this figure, by increasing titanium nanoparticle concentration up to 0.9 gram per liter, more than 80% of TCE was degraded. However, further increasing titanium concentration have a contrary effect on the TCE degradation efficiency. Medical applications including drug delivery, cancer therapy, bio and pharmaceutical, functional tissue, cell interaction, and magnetic hyperthermia therapy are the last applications of nanofluids mentioned here. Now the most important challenges of producing and using nanofluids will be explained. The development of nanofluids is hindered by lack of agreement of results obtained by different researchers, poor characterization of suspensions, lack of theoretical understanding of the mechanisms responsible for changes in properties, industrial-scale production of nanofluids, narrow range of operating conditions, include pressure drop. The production of nanoparticles and nanofluids is expensive. Higher production cost of nanofluids is among the reasons that may hinder the application of nanofluids in industry. Thus, nanofluids at this material cost will only be used in application and devices that have high profit margin to justify the significant additional cost and use small quantity of nanofluids. The production and use of artificially engineered nanoparticles is a very recent phenomenon, and the effect of the engineered nanoparticles on the environment and the living organisms are still unknown. All of the available publications in this area recognize that the short-term and long-term environmental, ecological, and health effects of nanoparticles are largely unknown. It's found that the specific heat of nanofluids is lower than the base fluid. An ideal coolant should possess high value of specific heat, which enable the coolant to remove more heat. Preparation of homogeneous suspension remains a technical challenge since the nanoparticle always form aggregates due to the very strong van der Waals interactions. To get stable nanofluids, you may reduce particle size, reduce the density difference between the particle and the fluid, increase the viscosity of the fluid, using surface activator or dispersant, using mechanical mixing, using ultrasonic vibration. As mentioned, many investigations have been conducted on the various aspects of nanofluids behavior, but there are still several important issues that need to be solved for applications of nanofluids in engineering. Here are some suggestions for future works. Attempting to find the mechanisms of abnormal behavior of nanofluids, preparation of consistent databases of fundamental properties of nanofluids, developing suitable correlations for predicting the nanofluid properties and behavior, development of computer-based models of nanofluids phenomena, long-time experiment to check nanofluid stability and find out time-dependent factors, establish protocols for the preparation and preservation of fluid-solid mixtures, recommending appropriate instruments and protocols for the measurements of the transport properties of nanofluids, recognize that the distribution of the particle and the structures of aggregates and the clusters within the fluid mixture influence significantly the experimental data, develop models of nanofluids and nanofluid processes that include not only the physicochemical characteristics of nanoparticles and aggregates, but also the fluid-particle interactions. On the reporting of the enhancement of a property, always define what the basis of the enhancement is. Systematically question experimental data that do not agree with fundamental canons of mechanics, thermodynamics, and heat transfer. Reports and papers must contain all the necessary information that may enable someone else to repeat the same experiments. To the extent possible, archival publications should be complete and comprehensive. I'd like to end my presentation here. Thanks for your time and attention. If you have any questions, I'd be happy to answer them afterward.